Hi everyone, so today we're going to talk about the strain gauge lab. So in this lab we are going to again work with a aluminum cantilever beam. We are going to apply basically some deflection delta at the end of our beam. Actually not quite at the end, but we'll see that in a second. And we are going to measure the theoretical strain, which is given here, and also the experimental strain that we're going to measure using our again Wheatstone bridge configuration, basically half configuration of your Wheatstone bridge here. So this is kind of the schematic. Unfortunately, again, since we're in this kind of remote teaching mode, we're not going to be able to do this lab experimentally. But again, half Wheatstone bridge configuration, strain gauge on the top, strain gauge on the bottom. This is in your 1 position, this is in your 2 position on our standard Wheatstone bridge that we've talked about basically in previous videos. So we are going to apply some displacement, we're going to measure the strain, and then compare the theoretical and experimental strain as a function of this. We're going to apply this deflection of 0 deflection, 0.1 inches, and 0.2 inches. So let's get started on how we're going to kind of analyze and think about this lab. So I'm going to bring this over here, and I'm going to bring up my strain gauge lab right here. So we have this expression, delta is equal to your p times x squared over 6 times your Young's modulus times the moment of inertia. So let's take a look at this expression. We've got that there. We know that the moment of inertia for this cantilever beam is going to be equal to your base times height, which in this case is going to be again the thickness of your beam, and then all of this divided by 12. So this divide by 12, not multiply. And that's your moment of inertia. We also have kind of our strain theoretical, which is given here by P, or 6 times P times D divided by Young's modulus times your base. And you can kind of deduce this as well, times your height squared. This is for, again, if you apply it at the end of your kind of beam here. So, this is your strain theoretical. Now, I'm going to actually clear my delta for just a second. And you'll see why I'm going to do that in just a minute. But we know if we want to calculate, this is our goal in this lab, is to calculate the strain theoretical and the strain experimental. Now, we are going to apply a known delta. Delta is going to take on values of, again, 0 inches, 0.1 inches, or 0.2 inches. X is going to be essentially X is your distance here of the load or the displacement applied from the edge where the cantilever beam is placed. D is the distance from where the load is applied to the center of your strain gauge. And L is just the length of your beam. So again, we're going to know all these different values. So we know in this equation, we know L, we'll know X. We'll kind of define them in a bit. But what we don't know is P. We do not know the load. So we're going to have to calculate that. The load is going to change obviously for a given different displacement delta. So we need to kind of, if we want to calculate this strain theoretical, let's just plug in for P and rewrite this equation here, because we're going to solve for P. We know all these rest of these values, so let's substitute it in. So I'm going to take this expression here. I'm going to solve, just rewrite this in terms of delta P in terms of all these other variables. So solve for P. So P is this big mess here. So I'm going to substitute in for my strain, because we know I'm going to have to take some partials. So strain partials is going to be strain theory / dot P goes to, excuse me, just this. So that's my function. So now I have essentially my strain theoretical in terms of this value right here. So these are all my strain theoretical is a function of D, delta, H, X, and L. Now all of these values have some uncertainty associated with it. If you read the Mathematica notebook that is attached to this lab, you can kind of figure out what those uncertainties are. But we know if we want to figure out what is the bias error, we're going to have to take the partials. So I'm going to have to take the derivative of strain partials with respect to D, delta x h, and that's how you're going to calculate again the theoretical the bias error in this expression. So you have to do that for all of these variables here. So x, l, all that good stuff. Precision error in this lab. So for the theoretical component, again, we only measure these values once, so there is no precision error in the theoretical calculation of strain. So that's something to kind of keep an eye on or to note. So that basically takes care of how you calculate the theoretical or the bias error in the theoretical strain calculation. Now, we're working with an aluminum beam, so let's start to kind of tabulate some values. So 69 gigapascals is your Young's modulus for aluminum 6061, a good value to kind of have and memorize. The base of this beam is 25 millimeters. So I'm going to put that right here. My height is equal to 6 times 10 minus 3, so 6 millimeters of this beam. The length of my beam is 30.5 times 10 minus 2 meters. Again, everything here is in meters. My distance, d, is going to be equal to, again, distance is from where the load is applied to the center of the strain gauge. So that is going to be where the load is applied is 25.5 centimeters, or 25.5 centimeters, excuse me, minus where that strain gauge is located. So from the end of this cantilever beam here, from where 0 is, it is 9.5 away. So again, d is the distance from where the load is applied here to where the center of the strain gauge is here. So that's just kind of the calculation. 10 to the minus 2. And x is equal to 25. Because again, x is just the distance from where the beam is secured to where the load is applied. So that is going to be times 10 to the minus 2. That's it. So those are my values. I'm going to bring back delta here and work with that in just a second. So we have this. I'm going to plug in this value. And now we can solve for the load. So to solve for the load, solve where delta is equal to, for example, 0.1 inches. So I'm going to multiply this by meters to calculate inches. So if I apply a deflection, if I apply a deflection here, if delta is equal to 0.1 inches times 0.0254 to convert it into meters, solve for what is my load. That's it. That's your load in newtons. So again, you want to do this for all 0, 0.1, and 0.2 inches. And then you can calculate what is now the strain theory. So strain theory / dot P goes to this. That is your, essentially, your theoretical, your strain value here, excuse me, 0.0254. Yeah, so that is essentially the value that we're going to be working with. So now, here we get to the next point in here, which is we now need to calculate what is the experimental strain. So here, we are going to use the expressions that we've, again, let me spell it correctly. We're going to use the expressions that we've kind of deduced previously. So for a Wheatstone bridge, we have this expression that relates the change in voltage that we measure, so delta V divided by your excitation voltage, the excitation, that is equal to your gauge factor, excuse me, yes, F over 4 times epsilon, so the strain in the first branch minus the strain in the second branch minus the strain in the third branch of your 4 arms for the Wheatstone bridge, plus the strain epsilon in the fourth branch. So we know that we're using a half bridge configuration. So we know that this and this, epsilon 3 is 0, epsilon 4 is 0. Epsilon 1, which is misspelled, epsilon 1 is just going to be your positive bending, so strain and bending. Epsilon 2 is, since it's on the back of that beam, just like we kind of discussed in a previous video, that's going to be negative bending because we're compressing our strain gauge. So we're going to end up with the strain that we measure, the experimental strain, EB, is just going to be minus 2EB. So we're going to rewrite this expression. So the strain experimental, you're just plugging in for values here. We also know that your V excitation, so Vx equals 5 volts for this lab, again, seen in the lab handout. Your F gauge factor is going to be 2. And now we could rewrite this expression and solve for EB. You could just kind of write this as strain experimental too. Same idea. So bending strain, that's what we're kind of calculating here. Now, there might be some component of tension as well, or axial kind of strain, but we're going to assume in this cantilever beam setup, we're basically almost measuring exactly pure bending. So strain experimental is going to be equal to your change delta V divided by V excitation times 2 divided by F. That's it. So how do we measure this delta V, this delta V? Well, that's where we have to look at our data. So I'm going to bring in the data set here. And this is the data from delta of 0 inches. That's how you kind of read this data. So the delta of 0 inches, so when we didn't apply any deflection, this was the resulting voltages in millivolts. So we need to do a couple things first. So I don't like all these parentheses, so I'm just going to flatten. That just removes the parentheses. That's all this does. So I'm flattened out here. This data is in millivolts, so I'm going to multiply this times 10 to the minus 3 because I want to be in volts, everything consistent. So this is my delta, V, or you can kind of call it whatever you want, my delta of 0 inches. So this is that data. That's it. I measured this, obviously, again, we're taking it with the DAQs, we're making multiple measurements as a function of time, but this is your resultant voltage. Now, you might be asking, how are you measuring a voltage when you didn't apply any deflection? Well, when you first apply the strain gauge, you have to press really, really hard in order to kind of make it stick. So often you'll kind of read some resultant voltage from kind of pre-straining that strain gauge. So this is going to introduce some additional complications from just the theory that we've talked about. We're going to have to subtract from this. This is kind of like our baseline measurement. So without any deflection, we're reading this. So the delta V that we calculate for our deflections, we're going to have to subtract from this. I'll show you what that is in just a second. So I'm going to copy this. Instead, I'm going to do 0.1 inches, and I'm going to pull in a data point from here. Again, so see this dash is just like we've done previously. You're going to have 5 files, multiple files, so you're going to have to calculate precision error here. So make sure you kind of do that. Also, you're going to have to calculate, there's no uncertainty in this excitation voltage. There's no uncertainty in this F. There will be an uncertainty in the delta V you measure. It's going to be very small, typically like a microvolt. But again, you're going to have to calculate bias error for this. So take the partial of this expression with respect to this. The uncertainty here is about a microvolt. So really small bias error, but again, we need to account for that. So this is my delta 1, and I'm going to do the same thing for my delta 0.2. I'm just going to do this. Actually, excuse me, I think it should be, let me do 1A. Hopefully that works. Actually here, we're going to do this. This is already actually in millivolts here. So make a note of that. Here we go here. This is already in millivolts there. So that's it. So now all we have to do is go back in here and let's calculate what's the mean delta, delta 0 inches. It's this. You do the same thing for 0.1, 0.2. So we'll do 0, 1 inches. We'll do, actually put this at 0, 0, 1, and 2. So if we want to solve for what is our experimental strain, all I'm going to do is, if I want to do strain experimental, / dot, I need to do my delta V. Let's check that expression. Yeah. Delta V goes to, for the first, if I want to calculate the strain at a 0 delta, I need to do this, the mean of delta. That's my measurement, minus my baseline, which is just this. So as you might expect, the strain at 0 deflection is 0. That's a good confirmation. If I want to calculate the strain at 0.1, all I do is, again, what's my resultant voltage minus that baseline? It's this. And so on and so on and so forth and so forth. So again, that's how you would go ahead and calculate kind of these values. So that's what you want to kind of do in this lab. Remember, these are given already in millivolts, or sorry, exactly in volts here. So you don't have to multiply by that 10 to the minus 3. You do have to do it, unfortunately, with this first data set. And I'll make that clear in the, that should be clear in the lab mathematical notebook. So yeah, calculate your experimental strain, calculate your theoretical strain. For the experimental strain, we have precision and bias error. For the theoretical strain, we only have bias error. And plot those as a function of displacement, delta, and that's it. So on the y-axis, strain. On the x-axis, your deflections, delta, again, in 0.1 inches, convert that to meters. And that's it. See if those error bars overlap. If they do, then we know that those two measurements are indistinguishable. The experimental and the theoretical, correlate or they match. And yeah, if not, explain why that might not be the case. So that's it. Congratulations, you finished the lab component of this class. Make sure to write up that lab report and study for your final. And that's the end of the semester. It's been a pleasure. So if you have any questions, obviously still email, ask questions. If there's any other issues, if you want me to kind of go over more aspects of this lab. But yeah, that's it. Thanks. Have a great day.